Well, what have we done so far? Well, in our course, we started with Coulomb's law and then expressed it in the form of a surface integral with charge inside Q and arrived at Gauss's law. And Gauss's law is useful when you have cases of symmetry. Then we use special relativity and Coulomb's law to arrive at the magnetic field. A current in a wire produces the magnetic field, and the magnetic field lines wrap around the wire, unlike the electric field lines, which come out of the charge, so that if you enclose it, you have net electric field lines piercing through. Since the magnetic field wraps around the wire, then when you have an enclosure, you basically have the magnetic field lines on the inside, not coming out, or if some come pierce your surface, they go out the other side. So these circular magnetic field lines are going to give you zero when you do this kind of integral. We'll come back to that in a second and show you a magnet and how that works. Then we looked at a derivation of Faraday's law, where we arrived at it from our knowledge of electric and magnetic fields as well as the Lorentz force law. And it wasn't a, let's say, complete derivation, because these are really experimental laws, but I showed you how it would be plausible to arrive at this using theoretical approaches. Well, let's look at this second one here. And if we have the magnet that has a north and south pole, these field lines here tell you how the little baby magnet would point. If you had a baby magnet here, its south pole would hug the north and the north would go to the right. Over here, the north would want to go to the south, since the unlikes attract and the likes repel. And if you enclose this with a enclosed surface integral, you find that what goes in comes out. So here you would have outgoing magnetic field lines where you have the surface pointing, say, to the right, and this vector pointing to the right. That's positive contribution. But here, the surface would have a unit vector pointing to the left, and this would then go in the same value with the minus sign, and you would get zero. So if we had magnetic monopoles, if we had the north pole by itself and not the south pole, then you would have a non-zero contribution over here. But since there are no magnetic monopoles, or we haven't found any yet, the equation stands as it is with the zero there. This is almost the complete set of the Maxwell equations. We have to add a piece over here, which is analogous to this magnetic flux change. We want an electric flux change, and we'll be doing that in our next section.